Yes, please.
Okay, sir. Good morning, everyone. I, Dr. Kubernath Mishra, welcome you all to the second refreshing day of the Mechanical Engineering International Conference. The schedule ahead is as exciting as it was yesterday, and we have some globally renowned academicians with us to enlighten us with their pearls of wisdom. So let's proceed to the technical brilliance of the day. The first speaker of the session is Dr. V. Panduranga, a distinguished professor from the field of mechanical engineering. Dr. Panduranga is a professor in the School of Mechanical Sciences at the Indian Institute of Technology, Bhubaneswar, India. He earned his PhD in robotics and soft computing from IIT Kharagpur. Dr. Ranga's research interests encompass robotics, soft computing, and the modeling and optimization of manufacturing systems. Throughout his career, he has guided multiple PhD candidates and published over 120 technical papers in national and international journals and conferences. In addition to this, his academic roles, he serves as the Dean of Continuing Education at IIT Bhubaneswar, contributing significantly to the Institute's educational outreach and professional development programs. Now over to you, sir.
Thank you, sir, for your beautiful introduction. I'll be sharing my presentation.
So,
is my PPT visible?
yes, sir. You can make it full screen, sir.
Yeah, I'm trying. Yes, I hope it is in full screen now.
Yeah, yes, sir.
So good morning to you all. As introduced, I am Professor Panduranga Vandavelli from School of Mechanical Sciences, IIT Bhubaneswar. And I am here to give plenary talk on biped robotics and its gate generation. So the presentation contains the following topics: introduction, problem definition, so model of 70 degrees of freedom biped robot, DH parameter setting, kinematic relationships, dynamics, and the results of this method developed. So before actually jumping into this topic, I would like to brief the audience about what is a biped robot and what it consists of. So a robotic structure that resembles the shape of human being and capable of walking with the help of two legs is known as the humanoid robot. And its structure is very much similar to the human being, and it contains parts such as torso, head, legs, and arms similar to human being. So initially, this group or humanoid robots are developed by various research groups around the world to study and simulate the body structure and its behavior. The initial aim and objective was to build better orthoses and processes for the human beings. And later on, this study resulted in the development of mechanisms and structures similar to human being. Finally, the definition is as follows. The study related to the design, development, and fabrication of such structures is called humanoid robotics or biped robotics. As you see this animation, similar to human beings walk, the gait cycle of the biped robot also consists of two phases, namely single support phase and double support phase. We also execute similar type of walk. So most of our walk or this bipedal walk, the walking cycle is in the single support phase, and there is just instantaneous double support phase, whose purpose double support phase means on the stage in which both the legs are in contact with the ground. So this is just to extend the leg support and to move ahead. So when the robot is walking, so similar to our human beings walk, whenever we walk, we maintain our balance and stability during walk. Here also in its balance, there are the balance is very much important. So there are two different types of balancing criteria coming to the biped robot is concerned. That is static balance as well as the dynamic balance. So when we walk, we go in a dynamically balanced state. Similarly, so when the robot is walking, we are expected to see it is dynamically balanced. So when I said there are two different types of balancing aspects, static balance and dynamic balance, and I'd like to define what is it. The static balance is attributed with very slow walking. So during this phase, the robot is going to walk very slow, and during that phase, it is ensuring that the center of mass of the entire system is falling inside the put support polygon. Put support polygon means whenever we are walking with a single foot. So the center of single support phase. So this is assume your leg which is there in contact with the ground. The center of mass should fall inside the foot support polygon. So then only we say that the gait is statically balanced. And static balance is not so important for the biped robot because it is expected to perform the task at the desired pace like human beings. So then only we feel that the walking is happening in a real-time phase. So therefore, by biped robot walk is concerned, the dynamic balance is at most important. So it is defined like this. A robot is said to be dynamically balanced as long as the zero moment point is falling inside the foot support polygon. So here we are going to give introduce a new concept here, that is zero moment point. So it is a point on the foot support and the foot ground interaction, and about which the moments generated by various links of this robot are made to be equal to zero. So that point is called zero moment point. So very much similar to the static balance where center of mass is lying inside the foot support polygon. So in this case, when the robot is making a dynamic walk, its zero moment point is also should be falling inside the foot support polygon. So then only we will be able to say that the robot is dynamically balanced. So once again, this is the diagram which I have drawn. Assume that it is the support foot.
Yeah, now we are able to get your voice.
And
It's some network fluctuation.
Hello, is there any problem?
No. Now you are audible, sir. There was a network fluctuation. That's why.
So far, I'm not audible.
No. You were audible, sir.
Okay.
In between, we for a few seconds we lost the connectivity.
Okay. So as already drawn in the previous slide, so this is the foot support polygon, and as I mentioned, this is the location where the ZMP is acting. So then we can say that the gait is dynamically balanced. So once again, one more important parameter we are going to define, that is dynamic balance margin. So which will tell you the extent of balance. Say when this zero mount point is lying here and it is moving towards the end of the foot support polygon, and we'll be losing the balance. The moment the ZMP leaves this foot support polygon, we'll be losing our balance and we may topple. So for that, we have defined one parameter called dynamic balance margin, which will give an indication on how dynamically balanced the gait is. So this is defined as the distance between the point where ZMP is acting and the end of foot support polygon. So if it is exactly acting at the center, so then the dynamic balance margin will be maximum and the robot is maintaining its maximum balance or maximum stability. So whenever the point is moving towards the end of the foot support polygon, means we will be losing the balance. It is also true in the case of human beings. Whenever we are walking and unknowingly if we place our foot on a slippery surface or a peel of banana, so then the friction between the foot and the ground is not sufficient to retain the ZMP inside the foot support polygon. So then because of that, moments are not balanced and we will be just falling either back or forward depending on which direction we will be moving. Suppose if you are falling back, sometimes we will be just swinging our hands in the forward direction. So what are we doing? We are trying to regain our balance. So by providing moments in the opposite direction in which we are falling. The similar thing here also we will be implementing. So when the ZMP is moving out of the foot support polygon, we have to apply moments in the reverse direction so that the point will be pulled back inside the foot support polygon and the robot is going to maintain the balance. So these are various important vocabulary that we are going to come across this 20-25 minutes lecture. So this is the definition of the problem. So ascending, now I'm going to explain how to derive the gaits. Gaits means the sequence of steps involved in moving from one location to the another location. When we walk, how our leg make the movement. So that for 7 degrees of freedom bipedal, because that is the smallest number of degrees of freedom with which we can represent a bipedal robot, beyond which it will be little complex and it is computationally expensive. So therefore, I restricted my study or my presentation here to 170 degrees of freedom. So there are a lot of restrictions, but it will be able to execute walking in the direction of motion. It cannot take turn because the number of degrees of freedom is so less. It cannot take any turn. We have restricted the motion to move in only one plane. Sorry. Yeah. If you see, this is the stick diagram of the biped robot walking or moving on a staircase. If you see, there is one stair. Now I am drawing with the red sketch. So this is the staircase on which there is a robot moving. The robot is a 7 degrees of freedom, which is having 7 legs, which are darker, appearing darker on the slide. So there are so many lines in this. So this is 1 foot. And this is the lower leg of lower portion of the leg, upper portion of the leg, one leg, and the second upper portion and lower portion. Okay, and the foot, and this is trunk. So this is the 7 degrees of freedom robot, and here at this junction we will be having what do we call 3 joints. Like one leg will be coming like this, another leg will be coming like this, and there is a joint, and here one joint with this leg, another joint with this leg, one joint with the trunk. So as it is a side view, so all the joints, 3 joints are at the single location, and rest here there is 1 degree of freedom, and at the another knee joint another degrees of freedom. Here one ankle and another ankle. So therefore two at two different ankles, 2 at knees and 3 at the hip. So total it is 7 degrees of freedom. So this robot like this it can move on the staircase. And if you observe this diagram, one more important feature is that there is one curve, that is a trajectory that represents the swing foot motion. So like whenever we are also walking, we will be carefully lifting our foot and placing in a safe zone. So whenever there are stairs, whenever there are obstacles, whenever the terrain is not so uniform, so we will have to place our foot carefully to avoid collision with whatever the objects that are present in the terrain. So in this case, we have assumed a cubic polynomial so to be followed by this swing foot, so that this foot is going to avoid collision with the stairs present in its way. Okay, so these are various important things. And one more thing is that here if you see there are masses mounted on each link at point masses. This is called lumped mass system. Instead of going for uniform distribution of mass, which will be computationally expensive to determine various parameters of the link, we have assumed lumped mass system. And so one important thing, whenever we are walking, our legs are going to make some relationship with our hip. Here also this hip joint is going to make certain relationship with the end of this foot supports. Here, so this leg support and this leg support. The included angles made by these this leg and the two parts of these two legs are going to make a relationship with this hip. That is the distance, that is the length, and this one. This is the length L1 and height of the hip joint from this swing foot. Similarly, the height, the length L2 and the height H2 of the hip joint of the support. So with this, we will be able to achieve the gait by following inverse kinematics. Those who are working in robotics, so they will be able to understand what is inverse kinematics, or using the trigonometric approach to obtain the included angles made by these four joints, theta 2, theta 3, theta 6, and theta 5. Okay, so then this is how the DH parameters are assigned, like at various joint, in order to establish the relationship between the motion of various links. And with that, we have extracted the DH parameter related to this robotic configuration. This is twist of the link, length of the link, joint angle, and joint offset. These 4 parameters in order to derive the forward kinematic matrix, it is required. So then, as I explained, this is the equation that represents the cubic polynomial trajectory for the swing foot. Here we are going to establish the boundary conditions so that we will be solving the coefficient C0, C1, C2, C3. So there are 4 unknowns. By applying 4 boundary conditions, we will be having 4 simultaneous equations, and by solving those, we will be getting C0, C1, C2, and C3. Here are the boundary conditions, 4 boundary conditions with respect to the terrain, dimensions, the geometry of the terrain, so that we will be able to get the coefficients and we will be able to establish the relationship with which the swing leg is moving. And I already mentioned theta 2 here in the previous slide. So theta 2, this is called theta 2, and this is theta 3, and this is theta 5, and this is theta 6. This is theta 1 here, and theta 7 here, and theta 4. Once again, this is theta 4. Okay. So these 3 things we have to derive. We already planned to derive theta 2, theta 3, theta 5, theta 6 by using the geometry or inverse kinematics. And if you see this theta 7, so it is resting on the ground. So theta 7 is assumed to be 0. So we left with, there are 2 unknowns, theta 1 to be derived and theta 4 to be derived. So they are the equation that represents inverse kinematics or by following the geometry or trigonometry. And then we have followed some algorithm. Actually, there are 2 unknowns, theta 1 and theta 4 need to be determined. So in this case, if you wanted to derive 2 unknowns simultaneously, we have to follow either inverse dynamics approach or semi-inverse approach, which is computationally expensive. So we thought of eliminating this inverse process and adopted a simple algorithm in a forward manner. So in that case, what we did, we assumed the trajectory for the center of mass of the system, and based on that we derived theta 4 and theta 1, which we are calling that is swing foot trajectory, that is theta 1 is assumed to be 0. So this is theta 1 making 0 with respect to horizontal and throughout the motion. So whenever it is moving from one location to another location, so it is moving like a flat footing. So of course, it was slightly consuming more energy, but in order to save this computational complexity to avoid inverse dynamics approach, we made it 0 and we tried to determine only theta 4. So if you get the theta 4, so then all the gate angles are derived, and with this the robot can be moved. So theta 4 is derived by assuming a trajectory for center of mass. Based on that, we will be getting theta 4. So the angle, included angle made by the trunk, for which the location of center of mass is given with the theta 4 is calculated. So theta 1 is 0, theta 7 is 0, theta 2, theta 3, theta 5, theta 6 are calculated by using inverse kinematics, and theta 4 with the help of this trajectory of the center of mass. So once this entire gate is generated, and my objective is to see that the gate generated is dynamically balanced or not. So for that, what we did, we have calculated the location of ZMP by considering the motion for various joints, and from that we determined what is the DBM value, dynamic balance margin, which is the distance between the point where ZMP is acting and the end of foot support polygon. Then we derived the dynamics using Lagrange-Euler formulation. So here we try to determine what is the torque required to establish the desired motion by various joints by following Lagrange-Euler formula, which is nothing but the Lagrangian is the difference of kinetic energy and potential energy of the entire system. And so these are this is the final equation of motion that represents dynamics derived using Lagrange-Euler, tau I, torque required at joint I. And here there are different terms, DIK, HIKM, and CI. So these are inertia terms, Coriolis and centrifugal terms, and gravity terms. Okay, with this we'll be able to derive the equation of motion, and then we calculate what is the actual power required in order to drive this robot in one complete cycle. Okay, with this ends the formulation, mathematical formulation for the biped robot while ascending the stairs. Now coming to the descending the stairs, the robot climbs and it has to uh, come down the stairs. So based on that, we have gone for formulating the descending stair also. But entire formulation remains same except a few differences. There are two major variations. One is the foot trajectory and the other one is motion of the robot. So coming to the foot trajectory, as once again it is terrain dependent, the equations are different. Earlier case we were climbing up, now we are coming down the stairs. Once again the geometry is varying, and based on the geometry we have got once again four boundary conditions to solve the four coefficients of the cubic polynomial. And then, so the important difference is that robot is moving in the direction of gravity. Earlier it was against the gravity, and it is in the direction of gravity. Plus g and minus g, the difference is there. So once the entire algorithm for ascending and descending the staircase for the biped robot is done, then we try to validate the algorithm by using some data which is taken in relation with the real human being. So these are the parameters for the for the 7 links: the mass, the length, radius, and the moment of inertia for the robotic structure. And so we try to calculate what could be the balance and amount of power consumption. So if you see these results, the robot is found to be more balanced. It is 0.02. Actually, we consider the foot as 0.5. It should be 0.025 maximum. But in the case of ascending, we have got, if it is acting at the center of the foot, it is 0.5. The ZMP is acting at the center. Ideally, it should be 0.025. But we have got some lower value. 0.0 means it is acting on either side like this. Okay, this is your dBm value. And descending it is 0.018. So if you compare this value, descending gate is having lower dynamical balance. And coming to the power, ascending gate has consumed more power. If you see these results, like whenever we climb the stairs, while ascending, while climbing up the stair, we feel little balanced. And while coming down the stair, we feel that we are not so balanced. We are moving in the direction of gravity. And similarly, when we ascend the stairs, we feel that we have consumed slightly more energy when compared with while descending, we feel almost we did not spend any energy. So those results, though the numerical values shows similar observation, and the experience is falling in line with the experience of the human beings while ascending and descending the stairs. So with this, we can conclude that whatever the mathematical formulation we did is okay to simulate the motion of biped robot on the staircase. So after that, we have developed the stick diagram, like how the biped robot is generating motion while ascending and descending the staircase. And this motion is also very much exactly falling in line with the experience of human beings. So this we can conclude that whatever the mathematical derivation, analytical method we proposed is fine when the robot is moving, climbing or ascending or descending the staircase. Thank you, sir. Any queries?
Sir,
Thank you, sir. Thanks a lot, sir. Any queries is welcome from the audience. Participants? So it seems there are no questions with the audience. But as a general audience, I would like to ask a question, sir. This
Yes.
out of my own curiosity.
Yeah.
I have a very rudimentary knowledge about robotics. So I would like to know, sir, apart from aesthetics, what exact application do we have for bipedal robots?
Bipedal robot, there are so many applications. Being we are humans, so we
Sir.
try to mimic ourselves. So that was the main theme. So that robot, the word robot first introduced in 1920 by Karl
Asimov.
Čapek. So there was a novel. So Rogers Universal Robot. So there also they assumed a robot like a human being. It like just looks like a human being and works for the human being. So based on that concept, people tried to develop, but they could not succeed because human body is such a complicated system. But after 40, 50 years, they were successful in mimicking certain parts of the human being and could make the industrial manipulator, which is having similar configuration from the waist of the human being, waist, shoulder, and this arm-like structure. So now we could mimic, and there are so many advanced versions of robots, humanoid robots. Honda has developed the most sophisticated Asimo humanoid robot. And after that, Sony has also developed. So many companies have developed so many applications. They're
Yeah,
sitting.
we came across Sophia in UAE.
Yeah.
recently.
Like that Robo movie. I used to quote this in my class. Rajnikant's Robo movie. So that is that will give enough information of what is humanoid robot.
Sir. Thank you. Thanks a lot, sir.
Thank
It
you
was
all, but the
really,
time is very short, 25
sir,
minutes. Given
sir,
general talks, I give 20-25 minutes introduction for this to introduce what is gate and introduce the important vocabulary. But the
sir.
session is so short, I try to just give some fragments of what is biped robotics.
कल
Future we
मेरा
will
आ
see.
गया नहीं जाते हैं कर लेते हैं लंच
Sir, my apologies on the behalf of organizing committee for limiting your speech to such a short
No,
duration.
I will come. Already I promised to your VC sir and Bhandarkar sir also I promised that
Sir,
soon we will
we'll be
plan it.
more than honored. We will be more than honored to host you, sir.
I will
Your,
physically want to
sir.
present there at least one day.
Yes, sir. Thank you, sir. Your insightful talk has highlighted that robotics and automation are advancing at never before pace, and they are bound to be crucial factor in Viksit Bharat 2047, sir. Sir.
Thank you.
Thank you, sir.
Thank you all. Thank you.
Thank you, sir. Thank you.
Thank you, Bhandarkar ji. Thank you.
Thank you, sir, for accepting our invitation, sir. Thank you.
So next we have with us a professor from the creamy layer of the top 2% of academic researchers. Please welcome our very own visiting faculty of the department, Dr. Satish Kumar. Dr. Kumar is a professor of the Department of Mechanical Engineering at NIT Jamshedpur. He earned his doctoral PhD degree from Indian Institute of Technology, Roorkee. Prior to this, he was associated with Thapar Institute of Engineering and Technology, Patiala. He specializes in computational fluid dynamics, erosion wear, and the study of solid liquid mixture flows in pumps and pipelines. With other 125 research publications, he is a member of esteemed professional bodies such as ASME and IST. Dr. Kumar has received numerous accolades, including faculty performance awards, and has successfully led funded research projects supported by DST and UGC. In addition to his academic and research contributions, he is actively involved in administrative responsibilities and currently serves as the chairman of several key committees at NIT Jamshedpur. With these words, I welcome you, sir, to start the session.
Thank you, Kuber. Good morning to all.
Good morning,
Thank
sir.
you
Good
for
morning.
nice introduction. And sorry for not meeting physical mode because in my institute also conference is going on.
Yes, sir.
Yeah. So, we don't know. Yeah. Just one.
Sir.
Entire screen. No? Yeah. This is visible, Kuber sir?
Yes, sir. Perfectly visible, sir.
Okay. So today I will discuss some key issues of the related to the CFD modeling of the pump performance of the industrial problem, which I have completed in one of my DST SERB research project. So topic is experimental investigation and CFD modeling of slurry pump handling non-Newtonian slurry flow. Uh, my introduction already given by the Mr. Sir, so I'm not discussing. This is the lab I have developed here in NIT Jamshedpur. Purpose of sharing this slide is to, if possible, participant faculty, we can make the collaborate the things for doing some experimentation, and also for the numerical work we can go ahead. So I am working widely on the computational fluid dynamics as well as the rheology of the fluid flow multi stage fluid flow suspension. Hello. Okay. Just so this is the problem related to the ash disposal system. मैं shift कर लूं? कुबेर सर, हेलो.
Yes, sir. Sir,
दो
your screen is.
2 सेकंड के लिए डिस्टर्बेंस, 2 सेकंड इंटरनेट का कुछ डिस्टर्बेंस है. जस्ट मैं फिर से लॉग इन कर रहा हूँ. जस्ट आई
You are
नीड
already logged in. Yes, sir.
ओके. जस्ट oh, sorry. So I have the very limited time. So in this work, what is the problem? Problem is the in I have taken the problem of the thermal power plant. Currently, thermal power plant, as we know, the coal we are burning in the thermal power plant, and after burning, produce the lot of the ash. So as per the government India norms, we have to utilize in many, you can say, areas for the fly ash as well as the bottom ash, but nowadays also we able to utilize only 45-50% of the produce ash in the different application, making the roads, or you can say utilization in the cement and other purposes, and rest of the ash problem is how to send into the ponds, ash ponds.
Yes, sir.
So हेलो.
रंजन जी को जो है अभी लेट होगा तो उनको उनके साथ कम्युनिकेशन है क्या?
रंजन सर के साथ कौन बात कर रहा है?
पहले आपका ये माइक बंद करो.
So this is the, currently in the thermal power plant they are transporting the ash with very lean mixture of the solid concentration up to 10 to 15%, and then research needs to improve the solid concentration of the transportation system, so that we can you can say we can you can say take the by increasing the solid concentration we can save the power as well as the water consumptions in the thermal power plant, and also reduction this help to minimize the environmental impact operation of the industrial purposes, because when this ash goes into the ponds, then metal concentration from the ash goes into the water, and nearby the people of the thermal power plant and the industries also affected. So this is the experimental setup of the centrifugal pump. So what we have done, this is the test loops, you can say diagrams. Here, this is a tank where we are mixing the solid with the liquid, and by the loop we are able to measuring the different places, flow concentration as well as the pressure drops. So first, what we have done for the modeling and simulation of the centrifugal pump, disassemble the all the component of the existing of the pumping is you can say slurry pump setup in parallel casing and other, and taken the dimension of the existing centrifugal slurry pump. This is called the reverse engineering also, with the help of plaster of Paris and then the other different applications. You have to measure the exact dimension of the pump, then the model 3D, prepare the 3D model. So these are the specification of the pump component. I'm not going in detail. So finally we have prepared the then after modeling of the all the in parallel casing as well as the passage of the pump, we have to join the all the components. Then this is
Sir,
the
sir, sorry to interrupt you.
yeah, yeah, yeah.
May I confirm if you are moving your slides on what slide number you are right now?
Or 6 7.
No, I think we are able to see only introduction right now, sir.
Oh, sorry. Just 1 minute. Second slides visible.
Now it is sixth. Now it is sixth slide, sir.
Okay. So
And
this
one more
form I can discuss.
request.
No.
One more request, sir.
Yeah.
May I request you to please hurry up a little bit, sir.
How much time you are giving so that I can conclude in between?
We have another 5 to 7 minutes, sir.
Time 7. Okay. So this
Sir.
is the
Thank you, sir.
no issue. I will try to complete within 8 or 10 minutes. So this
Sir.
is the pump assembly. So next work is to mesh generation of the pump component, and you can say perform the grid independent test. So for that purpose, this is a 3 type of the mesh generated A, B, C. In the A, total number of the nodes is 10,21,132. In B, 11 lakh.
I think we have lost your audio, sir. Sir. Sir, I think we have lost your audio. Sir, can you please rejoin, because we are neither able to hear you or not able to see you. Sir, may I request you to rejoin the session, sir? Sir, please rejoin the session, sir. We are unable to hear you or see your slides.
The pump with the water only. So simulation studies perform at the different 4 different RPM
Sir, we
condition.
are unable to see your slides, sir.
Oh, just 1 minute, sir.
Sir.
क्या? Sorry.
Now we can see you, sir.
Yes, sir. This is okay, sir?
Yes, sir. Now it's okay.
Then we have taken the 4 different speed: 1,000, 1,000, 1,150, 1,300, and 1,450 RPM. At the 4 different mass flow rate condition, you have to get the pressure values, and this is the head characteristics as well as the power input, power output, input power flow characteristics, and efficiency characteristics. Then we have to see the comparison of the experimental data with the numerical studies. So at the 4 operating condition, these are the deviation of the heads with the experimental data as well as the input power. Both deviation is very less, meaning is that our numerical investigation is, you can say, reasonable, give the reasonable good agreement with the experimental data, uh, as we have already performed. The next work is, we have to go for the outcome of the, you can say, flow visualization. This is important for the CFD simulation. So just you see, this is the graph. I am only discussing one, velocity distribution of the slurry pump impeller. We have taken at the two condition. One is the best efficiency point. Second is the off design condition at 0.2 values. And just you see, a good guidance of the flow we can visualize at the design condition. When we are going to off design condition, then here at the volute casing, lot of the circulation, recirculation, you can say vorticity generation is taking place, backflow you can say, which you can say, which you produce the lot of the losses, fluid friction losses in the casing section. So back, our work is we have to minimize this type of the losses by changing the, you can say, curvature of the casing. This is the simple conclusion for this investigation. K epsilon shows the very good agreement with the experimental result. Deviation with the experimental as well as the uh, experimental with the simulation data is coming within 5%. This shows the very good agreement with the experimental data. And this, you can say, this study we can go ahead by, you can say, optimization of the passes of the pumping by changing the different blade impeller thickness as well as the number of the blades. And by changing the volute section, we can minimize the recirculation losses. Then we have, just within 3 minutes I able to conclude. I'm not going to detail. Then my work is to conduct the experimentation with the solid liquid flow. So for the solid liquid flow, as we know, in the uh, two type of the model we are using, Euler Lagrangian model or Euler model. So I am not discussing in out of three why I have chosen. So mixture model we have chosen for the investigation. Mixture model means solid, liquid we are taking as a primary fluid, solid we are taking as a secondary fluid, and combined form of the addition form, you can say, of the conservation of mass, momentum as well as the energy equation we are using for the our investigation. So water has taken primary phase and solid phase bottom as taken for the secondary phase. And property of the all, with the, you can say, variation of the different concentration we have taken, you can say, calculated at all the concentration taken 15, 25, 35, and 45% on all the concentration. We have to measure the viscosity as well as the density of the exact density of the solid liquid suspension. Then you have to perform the mixture model simulation in the available the CFD software. So same things, same at the all the four speed condition, we have performed the simulation studies by using the mixture model at the different condition 15, 25, 35, and 45, and found that the maximum pressure drops comes 0.96 meter of the water column when we are going to move from 15 to 45% concentration, as well as the input power also increases. Other I am not going to discuss. This is a very important, you can say, flow visualization of the pressure distribution of the slurry pump with the water. Static pressure gradually increases inlet to the outlet. At inlet outlet to volute intersection, here at the interface sections, non-uniformity we are getting. So due to, you can say, flow divergence, backflow also we are getting, and solid move with the other velocity and liquid move with the other velocity. So we have to optimize the things of the volute section. Next is the volume fraction distribution of the bottom S. This is very important. So this is the distribution on at all the four concentration: 15, 25, 35, and 45. Just you see at the lower concentration, which actually presently thermal power plants are using up to 15% concentration, flow distribution is non-uniform. Just you see, these are the solid phases, and these are the different other colors are the water. So when we are moving 15 to 25, then uniformity increases, you can say. Non-uniformity of the solid with the water decreases. And when we are reaching up to 45%, then the approximately solid mix with the water and able to, you can say, homogeneous flow between the pump as well as the pumping section in parallel as well as the volute casing. So when the by this solid concentration inform the uniformity, when the inform unity, then you know when the solid particle impact on the metallic surface, then the produce the erosion wear also. So at the lower concentration you will get the more erosion. When you able to go up to 45%, then your erosion problems also will reduce. So outcome of the present work, we can by using this analysis, we can go ahead up to the higher concentration, 45-50% concentration. Now presently thermal power plant are transporting up to 15% water, and we can save a lot of the water and power for transportation of the solid materials. This is work done on the thermal power plant as disposal system. This work also can be, you can say, continue with the other trailing materials, just like iron ore suspension, coal in the thermal power plant, and disposal of the zinc ore suspension, lime water suspension, other waste disposal for the other mineral disposal system. This work can be utilized. And when we are transporting the able to transport the material with the high concentration, obviously we can save the water. And when we can save the water, meaning is that the a tracing element of the metal concentration also we can optimize and minimize the environmental impact of the operation. And beauty of this work is, without changing any modification in the design, we can able to you can say move ahead for the improve the performance of the our system. So this is the small discussion, 15-20 minutes. I look forward for the participants as well as the faculty for the different collaborative, if possible. Anyone can be visit of NIT Jamshedpur website, and Professor Satish Kumar can call, having the contact number also. Either write the email ID or call me. I am available for the any type of the discussion. So thank you, sir.
Thank you.
Thank you.
Thank you. Thanks a lot, sir.
Thank
So
you.
I would like to give a short message to the audience. In the times when the government of India and other non-government agencies are tightening their noose around the power plants and mining sector, so sir's research is going to be a pioneering work and is going to revolutionize the way the coal and the other minerals is going to be transported.
Sorry for a very small time not discussed.
We actually the apologies on our side, sir, because we
No,
were unable to provide you enough time to
no,
elaborate
no,
to
no.
put your work elaborately. So I'm really very thankful to Dr. Satish, sir,
Thank you for invitation
for
as well as the congratulations for the your
sir,
organizing very nice conference.
sir.
Thank you. I
Thank
will
you, sir.
try to meet physically when possible. Thank you, sir. Thank
Sure,
you.
sir. We'll be more than honored, sir, to host you. Thank you, sir.
Thank you, Kuberji. Thank you. Thank you.
So next on the panel, I would like to say carbon capture and storage is the single critical factor that may hold the key to sustainable and livable planet, as addressed in our inaugural session also. To elaborate further on this must-know technology, we have with us a specialist in this field. Please welcome Dr. Ranjan Pradhan.
Yeah, good morning. Am I audible and my screen is visible?
Yes, sir. Perfectly, sir. Perfectly audible and visible, sir.
Very good, nice. Thank you very much. And good morning, everyone, for joining here. And
I would like to interrupt you, sir. Let me give a brief introduction of for you to the audience, sir.
Okay, no problem.
Dr. Pradhan is currently contributing as Chief Scientific Advisor to Jindal Steel and Power for carbon capture utilization and storage projects, and is currently a special graduate faculty at the University of Guelph, Ontario, Canada. He is an alumnus of Gujarat University and has been actively involved in the field of microbiology and bioprocessing. He is a leader in carbon capture and an expert on biotransformations and biomaterials. He has extensive industrial research experiences and applied research, including scale U and commercialization. He joins us from Guelph, Canada. Sir, please.
Yeah, thank you very much. Okay, I go over to share my slides here. Okay, thank you again. And it's a pleasure to be here. So I'm the one I would be mostly talking about the sustainability part of this conference. I think you may have some more speakers on this, but I like the title of this conference, Advancement, Innovation, Automation for Sustainability, which indicates to me is everything is directed towards sustainability. So it's a good job to address that. And my title of this talk is energy efficiency still worthwhile for a sustainability goal? So this is more of an information sharing talk, and I'm trying to share as much information to drive some sustainability goal thoughts and bringing in energy efficiency into the arena. And we'll be going over this energy efficiency and sustainability goal in a little deeper. So the next slide tells us about the sustainability development goals, and it would be useful for younger researchers if you are not aware of it. Please do review the United Nations sustainability goals and their objectives. And this has been developed ever since like in 2015 when COP21 was evolving. And after that, they identified 17 goals. Those are called Sustainability Development Goals, and in short, are referred to SDG. And these are all directed towards having a future Earth that is more sustainable and habitable. There is serious concern about it. There may be different opinions, but trust me, this is a serious concern and need to be addressed now than later. And I'm proud to say that Jindal Steel and Power has demonstrated excellence in committing to SDG. 16 of those SDGs are adopted by JSPL and out of the 17 ones. And we are also partnered with Government of India in many of these supporting programs that government does. JSP is also a leader in carbon capture and CCUS technologies in India. And I'm proud to say that we are an innovation-hungry organization, and we remain committed to welcome any potential technology trial opportunities in CCUS. So this is just to update about the organization. And coming back to the question, so then why is there a question, is energy efficiency still worthwhile for sustainability goal? It's very obvious, okay, that energy efficiency is worthwhile for so many things, but do we drive ourselves to that to reflect as sustainability goal? Because there are so many distractors on the way. The number one is if we understand sustainability goal is so huge, then we'll come up with situations where we'll doubt ourselves, where we would say energy efficiency seems so small to the overall need of the climate change goal. So that forces us to question the effective contributions of ourselves. So this title conveys two contexts that are science-based and fact-based. So
Sorry
one
to
is
interrupt you.
Yeah, sorry.
But are you presenting from some presentation?
No.
I mean, we are unable to see any slides or any presentation right now.
Yes, its slide is shared. I don't know.
The
Oh
screen
my God.
sharing. I guess you have to
Okay,
share the
it's
screen.
yeah, I think I shared it when okay, earlier when I shared it, it didn't work, I think. Okay. I'm so sorry about that. Screen shared. Do you see it now?
Not yet, sir.
No? You don't see the screen, right?
No, sir.
Yeah. Excuse me. Can you
Yes, sir.
can you see the screen by
Uh,
any chance? Because I
no,
did
sir.
share.
We are able to see you, but not your slides.
I'm joining from the browser, so I don't use Zoom so much.
Okay. So there is between question and answer and raise hand, you must be able to see share.
No, I see that. I do that, but it
Sir.
says share entire screen, and I do share that. No, I have that on. It's not allow share window. So this window is there. Can I just email you the
Yes, sir.
slide and It's just
Please share it
doesn't
with
work.
Dr. Bhandarkar. He will play the slides for you, sir.
Okay, that should be quick.
So I request the audience to bear with us for a few moments until we overcome this glitch.
Yeah, then there has been multiple disturbances today. I hope it went good yesterday.
No, it's still fine, sir. Things like this keep
Oh,
happening during online meetings.
no, but somehow, yeah, because for me, it's the system that doesn't let Zoom somehow, maybe.
Sir. Maybe your browser doesn't allow, sir, pop-ups.
Yeah, it's Safari and I don't.
Safari, yes. So because of
Yeah,
safety issues, it does not allow pop-ups actually.
yeah, that's maybe the issue.
Yes, sir.
It should
That seems to be the issue.
because we can do the communications. It's just okay.
Yes, sir.
I sent the
Dr.
file.
Bhandarkar will. Yes, sir.
Yeah, I did send him.
So in a moment, I'll be back. Yes, sir. Now I guess we can start.
Yeah, sorry, viewers, and sorry, and I would try to be quick, and so that we don't lose any more time. So yeah, we can ignore this page, please. So it's the question, it's the title page. So next slide, please. Yeah, so as we were saying before, this is the sustainability development goals. So yeah, it can be on the last slide so that the people know actually where they want to fight. I'll just like go.
Previous slide.
So yeah, the previous one, please. More seconds. We'll go from the second one. Yeah, the sustainability goals is like now important. I have seen students that struggle to know sustainability goals because we as researchers need to know sustainability goals that world is striving to align themselves. So our research needs to be aligned and should address all these goals. If needed, they should present and try to point that out that this research is directing towards this or helping towards this, that would be a good catch there. And as I said before, Jindal Steel is doing all that it can do with aligning with 16 of these SDGs. So next slide, please. Yeah, so this is what I would like to play this context of this question is, it's partly a sarcasm, so that I offer you some more information towards it, and partly a serious food for thought for the researchers, so that we can drive ourselves towards climate emergency. So the sarcasm is on Jevons paradox, and we'll discuss that out, and then we'll go over to climate emergency. So next slide, please. So what is energy efficiency as we understand it? It's just plainly the using less energy to perform the same task. And the examples would be like LED lighting, or improving building insulations, or using fuel efficient vehicles, or employing efficient manufacturing processes. And is energy efficient is still worthwhile if the cost of that same thing is high? In addition to low GHG emissions, are we addressing affordability and profitability? For example, if we buy a AC and it's energy efficient, do I help climate or my bills? So these are the issues that come up. So we need to target those. So next slide, please. Next slide, yeah. So this is where the Jevons paradox comes. And what is Jevons paradox? Way back in 1866, Jevons wrote a book that said, Coal Questions. There he discussed about coal. At that point, what happened was during the period of 1710 to 1860, the steam engine efficiency improved by 8 times. However, it caused rise in coal use by 18 times instead of expecting a fall. So the discussion went through to conclude the efficiency improvement can sometimes lead to increased consumption rather than intended conservation. So we'll elaborate this further. So are you getting the paradox here? So we we increased efficiency, and we in turn spend more or use more. So for instance, LED bulbs, as I quoted before, invention of LED bulb drove widespread adoption of these bulbs because of low wattage. However, overall energy consumptions did not decrease. Why? Because reduced cost of light unit has prompted people to install or use more lights for extended periods. Additionally, proliferation of outdoor light products came up, and additional number of new lights in home also triggered. So this did it help reducing the power consumption? This is the paradox. Second, if you can say, the digital technology, same way, has benefited society, but has helped evolve many data centers and devices that increased energy consumption. So despite the improved efficiency of individual devices, the overall energy demand has increased due to the expanding use of technologies. So we can say, as technology get more efficient, we tend to consume more resources, and that's the paradox exactly. And this we can demonstrate ourselves also. You can judge for yourselves the productive time we have during high efficient mobile phones that we have and data network that we have. So judge for yourself. And to the next slide, please. So there are other distractors that also contribute to demotivate improvements. Like example, the net zero. Net zero is being targeted for 2050. But if we look through the net zero advantage, the benefits from net zero is so small to the cost of the net zero. So as you can see, it's 4.5 trillion of worth of benefit, but we have to spend annual cost of 26 trillions. Does it make sense? These questions do come up to create this confusion. And global share of renewable energy. You can see the plot. we were almost at 100% renewable energy using people. And as we progress, because the renewable energy could not be scaled up, we consume other resources. Now we are struggling to reach another 10% or percent higher renewable energy. So these are like triggers that takes our thoughts negative. Same way, global fire. In Canada, it's a um, high concern because there are a lot of fire, and there are in America also the fire is huge. And this comes to news and make us aware that so many fire happens because of the climate change. But actually what happens is when we reviewed satellite data, it shows from since 90s satellites were available to monitor this, and the trend is going down. Actually, the amount of fire happening in the land that is under fire is less. Even if it is projected with modeling in future, also strong climatic policy is not benefiting too much, and that it's a downward trend. So are we or should we be concerned so much about as it is played out? And there are climate misinformations. You can know that so many social media, even news articles do convey messages that are not very positive. A recent article in journal Nature has led to false allegations that researchers are exaggerating the impact of climate change. These are things that deviates us. So to the next slide, please. So please do not get misled, but stay informed. That's the only way we can address it. So science is clear. Energy efficiency remains an essential and worthwhile goal for sustainability. Now the question is, how significant is that? So energy-related GHG emission with or without efficiencies are plotted in the two plots on the bottom. And you can see when 2017 it was plotted, there was some benefits, but now when it was plotted, and you can see huge benefits can be derived with this, and we should be progressing ahead with these programs. Next, please. So we came down to the climate emergency that I would like to send the message across more. So what is the climate emergency and how emergency is it? It's just need to be in your back of your mind all the time. Even if we are doing research, it should address this because it is a climate emergency as of now. And how is it is the following slides would demonstrate that. So back in 2015 at COP21, the agreement was established that we'll be going for limiting global warming to below 1.5 degrees centigrade or below 2 degrees centigrade to pre-industrial level by end of the century. Please note the end of the century target. But see, as per India's meteorological department in 2024, India has had its third warmest November in 124 years of the average national average. And Northwest India had its warmest November, a record of 1.37 degree above average. And what are we targeting is 1.5 degree by end of the century, and we are in 2024. So, and global tipping points are even worse. The World United Environment Program has posted already that world is in a state of climate emergency, and we need to shift to emergency gear. And climate policies and energy policies need more support. Yeah, next slide, please. I'm sorry I have to rush a bit because of the shortage of time, but okay. I hope I'm doing good. Okay, so IPCC, that Intergovernmental Panel for Climate Change, in 2023 already posted that there are evidence of global warming underway, and the concentration of carbon dioxide unmatched for at least 2 million years. Glacial retreat unmatched for 2,000 years. Last decade warmer than any period for 125,000 years. Sea level rise faster than any prior century for 3,000 years. Summer Arctic ice converged smaller than any time in last 1,000 years. ocean warming happening, ocean acidification happening. So these are all fact-based monitoring systems that is working continuously. So they have posted this, makes us to think about how severe the situation is. World Meteorological Organization similarly have posted all this data, which are serious, and we are going to a severe issue. Yeah, next slide, please. So, like I mentioned earlier, there are tipping points in around the globe. There are 16 climate tipping points that are being continuously monitored. And it's not any publication or one research that comes up with this data. Huge amount of data are in place. And these climate tipping points are elements on the Earth system, which with small changes can tip a system from one stable state into a profoundly different state. So meaning irreversible state, and that would have cascading effect on other tipping points. So notice that 6 of these 16 tipping points are triggered below 2 degrees centigrade. That means if the temperature rises 2 degrees centigrade, these tipping points will give up and will impact all other tipping points and severely impact global ecosystem and global temperature system. It will affect practically humanity. Next slide, please. Next slide, please. Yeah, so this shows us these plots, how the temperatures are changing. I would like you to focus on the lower plot, which is the time lapse data for the temperature of sea surface temperature. And you can see 3 sections that goes back all the way to 400,000 years. And during that phase, it is so erratic temperature zone. But the human has been living the journey on Earth in the middle section, which is around more than 20,000 years back. And notice the temperature difference in there. So there is no abrupt temperature. It's a steady and calm temperature, which helped human or most of the living beings are currently on Earth to thrive. And thus the situation is optimum for us. And it helped to grow and flourish. So now we entered to the industrial era in the third zone, where we increased and went to a situation where the temperature has risen to 1.2 degrees centigrade. We have been there, but not as human. The Earth has been there. So human never experienced this zone earlier. So when in next few years or next few decades, we'll be crossing that zone where our ancestors have never seen that. So our future generations would be in a Earth that we have never seen. So that's where it's moving to. And that's real happening now. And if you can see the upper graph, is the sharp increase is very evident. From 1960s, it's going up, and the model suggested it would have gone 1.45 at that point, and we are close there. So the modeling says the same thing, the experience says the same thing. So we cannot go so wrong if we are projecting little far ahead from this. Yeah, next slide, please. So this was the 2024 that was projected after till from the up to October data. And at that point, it was proposed that 2024 is on the track of warmest year and the first year ever 1.5. However, lucky for us, this did not happen. And the next graph explains that. Next slide, please. See the top plot, the dark red plot is the data as of now till last week, and the data says it's way above any recorded temperature that we had experienced, and it was above 2023 almost till June, mid-year. So after mid-year, it went down a bit, matched up with 2023, but that's not a satisfactory zone that we want to be. This would be worse because it's above anything that we have been experiencing previously. And in addition to this temperature, there are other issues that is impacting also. And this global health would be impacted by the Earth system trends, which all of these graphs are showing a significant quick rise. And socio-economical trends are newly added trends that are impacting Earth system and our living conditions on Earth. So these are additional things to consider, not only the temperature, not only the CO2 level. So these CO2 level and temperatures are just indicators. So these multiple things that impact our Earth, there are uncertainties that how it would play out as we go further. Next slide, please. Next slide, please. Yeah. So what is it doing to us is Earth is losing resilience in forest system as of now. So like there are multiple reports, we can go on and on with the publications, and and there are numerous accounts suggesting that Amazon tipping is at the tipping point and would revert to a carbon emitting source rather than a carbon sink. Amazon is the largest carbon sink we have on the earth, and because of the deforestations and human activities and other calamities, it's very close because it's at 1.2 degrees, about 17% level for deforestations that we can handle. And once it crosses 20 to 25%, we would be in an ecological risk zone. And there are indicators that it's going away from being a sink to a source. And once that happens, it will impact so many ecosystems because it cannot manage, Earth cannot manage so much of impacts. Yeah, next slide, please. So we need to understand the resilience of Earth system and help support it. So what is the Earth system? There are 5 spheres in the Earth that are within Earth system. Those are atmosphere, hydrosphere, biosphere, lithosphere, and some cryosphere. And all these are very interlinked, and disturbances within any of these can drive instability. So there are tipping elements within all these spheres, and we can try to contribute the whichever way. Now the water hydrosphere is one. Before it was atmosphere, but now biosphere always was a concern. But the water has been a issue now. There's a free available fresh water is going towards the tipping point. So there are various models to study it, and we need to improve and adopt guidelines of models to remain on safe operations space on Earth. And one of such model is model like planetary boundary. I'll explain a bit more on this planetary boundary. This is one of the model. I do not say this is the model that we need to follow. There are several models, but for example, I'm taking this up. Can you go to the next slide, please? So these are the planetary boundaries as per Stockholm University's Stockholm Resilience Center. And this beautifully demonstrates that how it progresses. So in 2009, they came up with this planetary boundary model, and it served the purpose to explain at that point. They had 9 identified boundaries, and during that time, it was not a very big concern. Even then, 3 of those boundaries were out of the comfort zone of Earth, that we can say the safe operating space. The dotted circle on the center in the leftmost plot, that's the Earth's surface, and the green area is the safe operating zone, and anything that yellow and orange goes towards out of the zone or into a riskier area. So 3 of them were there. By 2015, then four of them were out of the boundaries. So, and by 2023, 6 of them were out of boundary. What are these? Actually, these are the biochemical reactions that fertilizers like nitrogen and phosphorus cycle are impacted. The climate change is impacted, biosphere is impacted, and land system is being impacted. So all these are out of boundary already. So what we are left with is just um, three boundaries, and from three, one of that is because of our human intervention that we have limited it. So that's the good part, that human interference is driving control of that. And so similarly, it is expected that if we can strive to do that, it can be controlled, but knowing and addressing those would be the key. Yeah, next one, please. So this graph is the news that we should be little bit happy about. What does this demonstrate is, you can see the upper portion of the graph which says emissions. The gray zone is the emissions that we do. That's the CO2 fossil fuels from industry. And the orange goes bottom, and under it is the land use change. So what happens is, up to 1950, before 1950, if you can see, it's narrow and suddenly it increases, and that's the industrial revolution that we know of. But what happens is the top and bottom are being complemented. And if you see, there is a mirror image like thing. So what is happening is the bottom portion is compensating or neutralizing those emissions all the time. So when Earth was started to be stressed by 1950, even the stressed Earth system tried to neutralize. So it has grown to neutralize till now. Even with so much of emissions, Earth system is trying to neutralize. And why are we looking at facing this global change, global climate change, or global warming, is because of the difference that we have on the bottom line. If we see that pink gray line on the bottom, that's the reflection of the top portion. So it's exactly the mirror image where it would fall. So there are some spikes bottom of that. Those are the outliers that did not get neutralized, and those are the portions that added up to make the earth warmer. So even with these tiny warming things have gave us about 1.2 degrees or 1.5 degrees. So we should not count on earth systems for long. So it would give up someday. It doesn't have capabilities to continue this longer, but at least we have a secure earth that is handling it nicely. So this is the global carbon budget that we want to manage. Yep. Next slide, please.
May I interrupt you a little bit, sir?
Yeah.
Okay, concluding. Okay.
Yes,
that was it.
concluding. Yeah, that's right.
Sir.
Yeah, I knew I was going fast. That's why. Okay, so what in concluding statement I would say is, currently the Earth is already about 1.2 degree warmer than it was in late 1800s. And IPCC also notes that to keep global temperature rise below 1.5, world needs to do net zero. UN says by 2050, IPCC says by 2050 to 2070. So clean energy is necessary, but not sufficient to meet the global goal of 1.5 degrees centigrade. And switching entirely to renewable energy is critical step towards achieving global climate goal, but it must be combined with changes in other sectors. So energy efficiency could deliver a reduction to annual energy related emissions, and delivering over 40% of avoidance required to be in line with the Paris Agreement. So energy efficiency alone can result in 40% abatement, and combined with renewable energy, other measures, energy efficiency is therefore the indispensable for achieving global climate targets. Next slide, please. And this is the end of the talk, where two of the SDGs do mention or influence or drive or motivate us to do energy efficiency. So according to United Nations Framework Convention, doubling energy efficiency by 2030 is the key to meeting global target. And there are so many ways this can be done. And one of the example is on the right side. Okay, next. Yeah. Next slide, please. Okay, yeah, thank you very much for the opportunity to present. I'm sorry we had technical issues, but I hope we could brief you up for something, and hopefully this would motivate you to contribute to sustainability.
Thanks a lot. Thanks a lot for sparing your time in the mid of the night, sir. I hope. I guess
Yeah.
it's 12:30 there, right, sir?
It's 1 o'clock, 1:10.
1 o'clock. My God. Really,
Yeah.
really sorry for bothering you so late in the night, sir. And we are really very honored and thankful to you, sir, for sharing the essence of your vast experience, updating us with the recent practices and trends in the steel industry, and truly contributing to the theme of this conference, sir. It was really getting interesting for all of us, but unfortunately, we did not have enough time to hear to you, sir. Thank you, sir.
Thank you. Thank you.
Thank you,
So I
sir. Thank you very
request-
much for your talk, sir.
Yeah, thank you.
I request the audience to move to their respective technical sessions for presentation of their papers. With this, we conclude this meeting. Thank you
Yeah.
all.
Thank you.